First of all, thanks to the organizers for letting me come to this very nice meeting. Today I'm going to tell you something about stuff that I've been doing for the past couple of years. I think some of you might have not heard this before. So Rupert already mentioned the Lyman forest, but it's good to go back to the basics for those of you who haven't thought much about it. So basically, if you see a bright background source in the high redshift universe that's emitting in ultraviolet, as the light goes through the IGM, you'll pick up traces of absorption from traces of neutral hydrogen in the foreground, and this builds up into the so-called Lyman forest absorption signal as the background source redshifts towards our telescopes. So basically, when we think about a Lyman forest, the kind of ansatz that we usually use is the so-called fluctuating Van-Pearson approximation. And so basically, to a first approximation, we can think of the absorption in the Lyman alpha forest as being some modulation of the underlying large-scale structure that's being modulated by astrophysics that's operating on it, and then it becomes exponentiated. It becomes exponentiated in the absorption. So basically, in this talk, I'm going to pretend astrophysics doesn't exist, and we're going to be thinking mostly of the Lyman forest as a direct tracer for the underlying density distribution. So, so there's this idea that's been actually floating around for the past 15 years. That's actually the first paper I can find for this was by Christophe Pichon by 2001, and I've actually been told that back in the day when people floated this idea, they were literally laughed out of the room. But basically the idea is that you have a set of IGM sidelines or quasars or whatever background sources you have, and if they're at sufficiently high density, you can try to reconstruct the 3D large-scale structure information on the scales of the sideline separation. So in this example, this is from a simulation. If you have the 3D absorption field, and you have a set of sidelines, even by eye, already mentally doing a tomographic reconstruction of this absorption field, and you can kind of see the same structures that you see in the full field. So we are used to thinking of Lyman forests as a phenomenon that we see in the sideline of quasars. So the reason that quasars work is because they have a bright ultraviolet. So there are bright ultraviolet sources in the rest frame, which allows you to pick up absorption in the 12-16 angstrom wavelengths. And the reason that we've been doing this so far is because quasar accretionists are the brightest UV sources in the distant universe. But if you're willing to go fainter, it turns out that star-forming galaxies are also bright sources of ultraviolet from O and B stars in their star-forming phases. So in this example, this is just an example SCD template. They do also have a bright UV background sources. So if you can pick them out, they can also act as Lyman forest backlights. And the reason that we might start thinking about LBGs, so just to step back, we usually refer to these things as Lyman break galaxies because of their method of selection. So the reason that we think about LBGs is because when we count the number of sources on the sky as a function of the magnitude, it turns out that, for example, BOSS has about of order 10 sidelines per square degree. Next generation of surveys on such as DESI with a 4-meter telescope might pick up about 25 to 40 per square degree. But if you push beyond, say, 23rd magnitude, you start picking up a huge number of sources that are from these Lyman break galaxies in the high redshifts. So if you can access this regime, your number of sightlines really jumps in the sky. So just to illustrate this issue, so this is an image in the cosmos field, and this is the standard unit for area of the sky, the full moon. So if I ask how many relatively bright quasars there are, say 22.5 mag, there are about 2 in this field of view. And if I go 2 magnitudes fainter and start picking up galaxies as well, you start picking up a huge number of sidelines. So there's a massive jump in the number of sidelines they can use to access this Lyman forest. So in the past couple of years, we've done a couple of studies where we look in simulations and try to do mock constructions with relatively realistic data. So this is a recent example from a paper that from Alex Trolevsky, who apparently is supposed to be here, but he isn't. But anyway, so
his flight is turned around halfway over the Atlantic.
Jeez.
He's coming back tonight.
Wow.
So this is a density field from the simulation, and these are a couple of examples using mock data, assuming different surveys. So for example, this is what we might do with something like the 30 mirror telescope, where the side lengths are about 1.4 megaparsecs over H, and you see that the reconstructed large-scale structure that you see here is almost identical to the underlying matter density. And here, this is a kind of survey that I'm going to talk about in a minute, and it's slightly more coarse, but it still has a good reflection of the large-scale structure. So in the past couple of years, we've been conducting a campaign on Keck telescope called Kamado. And the idea is to try to target the cosmos field, which is one of the best observed fields in the sky, and exploiting galaxies as background for sources for us to do IGN reconstruction. And so that's the telescope on the left here, and this is actually a very ugly this is a very ugly photograph. Can anyone tell me why? Clouds. So so far we've had about 50 hours of observations on sky, and again, this is the where we are right now on the data with the data. There's about there's about 230 sidelines at redshift between 2.2 to 3, and the footprint is, in terms of co-moving megaparsecs, is about 24 by 30 megaparsecs transverse. And so to show you some examples of the spectra, this is one of the brightest sources we have, which is a 23rd magnitude quasar, which is, most people don't think of 23rd magnitude as bright, but we do. And so this just to show you what like a typical LBG spectrum looks like. I'm just picked out a couple where you see the Lyman alpha emission line very clearly. But this is the Lyman alpha forest that we analyzed. So some of you might have noticed that these are extremely noisy data. And when you have noisy data, you put them into a sausage machine called Wiener filtering. So just like a sausage machine where you put random parts that you may not recognize or want to eat necessarily, the Wiener filter, you take all the noisy data you have and you toss it in. Hopefully you also have a noise vector, that's capital N, so that gives you a relative weighting between your pixels. And in our particular case, the correlation function that we assume, and so yeah, obviously for sausage you have a correlation function, which is the sausage skin. And in our case, the correlation function is just a simple Gaussian. So we assume a Gaussian that's roughly the same scale as our data, a couple of megaparsecs. So this is our data. So this is real data, by the way. This is not simulation. So the blue blob is basically our data. The dots are galaxies in the foreground that's compiled from different surveys. So we're flying towards Earth now, and yeah, so it's slightly blobby here. But anyway, so the first sanity check is, well, the galaxies and the absorption do more or less trace the same structures in the cosmic web. So in particular, there's this massive superstructure of both gas and galaxies that's extending about 80 megaparsecs, from moving at redshift 2.45 to 2.5. We're going to talk a little bit about that in a second. That's where we are right now, but I think we really are starting to directly map out the cosmic web at redshift 2.5. So again, this is another view where I'm just kind of stepping through a tomographic slice. This time, again, this is the plane of the sky. This is now a slice of the map, where this is the direction. So it's this slice projected along the redshift dimension. And now I'm going to step through the map in slices of RA, and you can see again that we basically do resolve large-scale structure at high redshift. So one of the interesting things that we've been looking at are a system of galaxy protoclusters that have been detected in other surveys, and we do see kind of the large overdensities and filamentary structures. So this is again my map, but sliced in a thin slice of delta Z, centered around a couple of these high redshift clusters. So we're kind of going to analyze. We're analyzing these systems right now, but eventually we want to do a full initial reconstruction of initial conditions in this system. Another thing that one can do with the Lyman forest is to do the cross correlations between the foreground galaxies and the background and the Lyman forest. So we've compiled something like 1,400 galaxies in the foreground of the cosmos field at between redshift 2.0 to 2.6. So this is a big alphabet soup of galaxies. And so the idea is that if you measure the cross correlation between the galaxies and Lyman forest, and if we can model it, as basically the cross power between the galaxy and the Lyman forest, on top of some underlying linear cosmology, and it turns out the Lyman forest multiplied by the RSD of the Lyman forest is known to basically a couple %. So we can fix this and use that to constrain the bias of the foreground galaxies. So that's kind of what we're currently doing. So these are kind of the cross correlation. This is the line of sight, and this is the transverse, where we've split up by the spectroscopic surveys. So we're used to thinking of spectroscopic surveys in the spectroscopic redshifts are perfect, right? It turns out they are not. So, for example, with something like Z Cosmos survey, there, if things going on where, like, for example, all the redshifts are systematically biased by a few megaparsecs along the line of sight. But so far, we have something like an 18 sigma detection across all our samples in this cross correlation, and we're hoping to get our results out in the next couple of months. And another fun thing one can do with this map is to try to look for cosmic voids at high redshift. So currently, the most distant cosmic voids are from Viper survey at redshift of about 0.9. Now we're looking for cosmic voids at about redshift 2.5. So even by eye, you already see kind of these underdense regions in the map. And right now we're writing a paper. We're trying to validate the significance of this by cross-correlating kind of with the foreground galaxies. So we basically look for voids, and then we do the very this kindergarten level analysis of basically asking, if you take the voids and you count the number of galaxies that fall in the voids, and then you randomize the voids, how many of the randoms actually have the same number of galaxies as the voids. And so this is an example. The red curve is the randomized distribution with some number of galaxies within the voids, and the blue line is where it is in the actual detected void distribution. So this directly gives you the p-values just by counting to the left of this. And so right now we have something like cross-correlating with this alphabet soup of surveys. We right now have something like 4.4 sigma detection of cosmic voids at redshift 2.3. So I'm basically out of time. I'm just going to say a minute about where we're hoping to go with this. So in the next few years, there's this big giant spectrograph on the Subaru telescope called the PFS that's gonna is several full moons worth of targets in one go, and eventually we hope to get something like Viper's-like volume at redshift between 2.5 and 3, and this will really start hitting cosmological volumes. But then the next step beyond that, so Rupert was giggling at this at MSE, but this is even crazier, which is the so-called billion object apparatus that we're starting to think about. So this is going to be a 10-meter class survey telescope with a wide field and a multiplex of about 25 to 30,000. And it's basically just the spectroscopists wondering, like, well, what can we do with the LSST-like budget? And basically, the goal of this program is to get something like close to 500 million galaxy redshifts over 10,000 square degrees. And also, that's going out to about, say, redshift 1.5. And also, for my interest, is to get something like 20 million background LBGs to do IGM tomography over half of the sky. So I am going to skip. I like to do this. So the goal of the BOA is to get all the cosmological information in the sky. So I'm just going to leave out my summary slide and take questions.